problem 3. So here we are kind of continuing or using the transfer function from problem 2, ys by rs. So we already have that from our earlier solution. We are going to compare that with the standard form for second order transfer function. And as you guys know, we can compare the terms in the denominator to calculate our natural frequency as well as the damping ratio. So we'll do that again. And then as far as I remember, Dr. Goen kind of gave you this table as well in the homework. So what we can do is just plug in those omega n and zeta values in these expressions and come up with a list of parameters for this system, right? And then I'll go over a MATLAB script as well and see what our answers look like compared to what MATLAB gives us with the step command. So let's start off with omega n. So as you guys know, we can compare those two terms. So natural frequency would, for this case, turn out to be root of 28, which turns out to be around 5.29 radians per second. And then we can compare the coefficients here. So that's 4, and that should be equal to this 2 times zeta times omega n. So our damping ratio would be nothing but 4 divided by 2 times omega n, plugging in our value, and this ends up being around 0.378. So now that we have these two variables for our current system, it's basically just plugging all of these into these expressions and getting these parameters. So what I'll do is I'll just write them down, the answers that I got for those, and then we'll kind of go over and see what happens in the MATLAB script. So for our maximum percent overshoot, for this case it turned out to be 27.7%, and then the peak time, this turned out to be around 0.6413 seconds. The delay time around 0.239, and then we have our rise time. Keep in mind that this is 100%, so it's the rise time is basically denoting the time it takes to go from 0% to 100%. That's the expression that's given there, and this would give us dr as 0.399 seconds. And then finally we have our 2% settling time. Now for this particular case, we guys know that the product of the damping ratio and the natural frequency turns out to be just 2 from just comparing the denominator of the standard form and the transfer function that we have. So we can just use that 2 factor here directly, and we end up with 2 seconds. That's our settling time. So now let's try to run our MATLAB script and see what answers MATLAB gives us. So I'll be posting this on Carmen as well, so don't worry about that. Alright, so I'll run this once again. So as you can see, we have set up the transfer function just as we had, right? And then when we use our damping function, it gives you the damping ratio as well as the natural frequency. It's the same as what we had evaluated as you guys remember. And then when we use our step and step info functions, you get the rise time, transient time, settling time, all of these parameters, and you can compare these with the values that I just shared. So they're really close. And there is some differences, because this is being evaluated numerically. Maybe they're using a slightly different method. So some differences are okay, but you will see that your answers are very close, almost matching. And you can see that if you want to change the argument or the rise time limits, since this is going from 0 to 100% and not the standard 10 to 90%, you can change that by using that flag in your function input. And again, I'll be sharing this on Carmen. You can run it. If you have any questions, let me know. All right. So going back to